Hello, good morning, guys. Welcome to the next class. And now that we have done uh, Fresnel and Fourier diffraction, Fresnel and Fraunhofer diffractions, we may now start looking at how the principles of Fourier theorem can be applied to optical systems like image formation and diffraction. Just like what we have in optical frequencies in the time domain, we can also have an equivalent uh, as called spatial frequencies when we consider uh, uh, images, for example. And in a sense, or actually, the diffraction pattern is a two-dimensional intensity distribution on a screen. And therefore, what we are dealing with is the equivalent of frequency in the time domain, which we call spatial frequencies. Then the primary motivation will be to develop understanding on the way optical systems process light to form, let's say, images, and also on diffraction. And we should know all about the amplitudes and phases of light waves reaching the image plane. In the last few classes, we have been using the Fresnel-Kirchhoff formula or the approximations of Fresnel-Kirchhoff formula to find the field distribution on a screen. Now we are going to use the principles of Fourier optics or Fourier transform to see the intensity patterns on a screen, diffraction patterns or images, and all these things. We'll start with some basics of Fourier transform. We know this, and you have learned this, I suppose. The Fourier transform of a function fx, which is a function of x, a one-dimensional function, is defined as, if you represent the Fourier transform by capital F of k, then it is the integral minus infinity to plus infinity of the function fx multiplied by e to the pi ikx, and the integration over is over x. It is as simple as that as an expression. Now, you can also, if you know the Fourier transform of a function, you can find the function itself by something called inverse Fourier transform, which is almost exactly the same with only plus I replaced by minus I, and the integration is over k. Here, what you may see different in different textbooks is this constant. Somewhere it could be 1 by 2 pi, sometimes it could be divided between this 1 by square root of 2 pi and 1 over square root of 2 pi, etc. Square root of 2 pi, etc. But the functional form here will and should remain the same. Okay. And symbolically, you can represent f of k as a curly f of fx. If you see this, it most probably means the Fourier transform of the function fx. Now, Fourier transform is, in general, it's a complex function, ak plus I bk, and there where ak is fx cos x dx, integral minus infinity to plus infinity, and the imaginary part is the function multiplied by sine kx dx and integral over minus infinity to plus infinity. These are some of the definitions which we assume that you are familiar with. Now, as I said, if it's what I'm trying to say here is the equivalence of the variables time and space variable. You can have a function of t, you can have a function of x, then with x changing to t, we replace k with omega. This is your spatial frequency, this is your frequency in the time, angular frequency in the time domain. Then we will have a similar expression for in to convert a signal in the time domain to a signal in the frequency domain and vice versa. This is your Fourier transform, and a function time domain is converted into a function of Fourier angle frequency or frequency domain by this process, and the inverse can be done over this one. And if a function fx that we have considered here is a function of a sum of two functions, like if fx is f1x plus f2x, then fk, its Fourier transform, will be the sum of Fourier transforms of the component functions, or in other words, if you want to write like fk equals f1k, the Fourier transform of the first function, plus f2k, Fourier transform of the second function. That is a basic principle of basic property of the of Fourier transform. For example, if you have a step function, not a step function, it's a square wave, a square pulse like this one, and if you try to Fourier transform it, this will be like okay, this is, if this f1k, it's a sinc function having certain width. Now, as a second source or a second aperture or whatever function, if you have a slightly wider step function, wider square function like this one, then the Fourier, okay, the Fourier transform will be a sinc function, but it will have a significantly lower width. This width will be narrower because this is wider. Okay, you can actually do it if you know MATLAB or Origin, or even I think you will be able to compute it in Excel if you like. Now, suppose you have a function like this one. It is f3 is the sum of the two functions. Okay, you add this function to this function, and you get something like this. It's straightforward. Sorry, this. Okay. Then what the property says is that the Fourier transform, okay, it will be okay, only have the main lobe. Okay, this is the first one, and then okay, it may be something slightly different from this one because you are trying to add. Then the smaller one is this one, and when you add the two, you get, and the Fourier transform will be this one. And therefore, okay, that one proved. You can also apply this to two-dimensional cases, which is more realistic in the sense that in the case of images and also in the case of diffraction patterns. and these are often encountered in optics. This is given as an example. Now here we have a function f of xy, and that is Fourier transformed through this. Instead of for a single dimensional function, you should have had only this one. Now since it's a function of x and y, you have e to the power I kxx multiplied by e to the power I kyy. Then instead of having dx only, you can have dx and dy. That is the two-dimensional Fourier transform. And in this case, instead of having 1 over 2 pi in the initial, in the one-dimensional case, you could have 1 by 2 pi square, all square, and kx, ky are the angular frequencies, angular spatial frequencies along the two axes. And fxy can be constructed out of a linear combination of elementary functions having this thing with the proper amplitudes, weighted amplitudes and phase by a complex factor f. Okay. This will give you the amplitude and phase of the function, and the function form of the functions that makes the combination will be e to the power I kx and so on. Now if you want to visualize it in the case of diffraction, okay, in this case Fraunhofer diffraction, because we have plane wavefronts coming from the left, and then you have an aperture, and the light travels through the aperture, and the emerging wavefront, okay, you'll have wavefronts. The emerging wavefront is a superposition of plane waves coming off in all directions. Okay. Because you can consider this as a plane wave that is coming off in this direction. Here you have a plane wave, this is undeviated field. Then here you can have a plane wave, or you can consider this actual wavefront here as a superposition of this spherical or whatever wavefront you're going to get here. The resultant will be the superposition of this plane wavefronts, and these plane waves are Fourier transform components with specific values of angular spatial frequency. Okay. And by the addition of or the superposition of all these Fourier components, you will get the actual wavefront, or you can reconstruct the actual wavefront. And in this case, the zero spatial frequency corresponds to undeviated beam, and higher spatial frequency, higher angles from the central axis, and so on. And these Fourier components actually makes up the diffractive field. Now, as another example, let's consider the lens as a Fourier transform. And in this case, again, we have a plane wavefront that is and an aperture that's going through an aperture here with which is on the back or the front focal plane. Okay, let's say this is your front focal plane. Okay, this is your back focal plane, and this is your front focal plane. And in this case, why it is called front and back? Because it's at a distance f behind the lens itself, and this one is at a distance f after the lens, and this is the focal plane, which we also call the Fourier plane of the lens, which we demonstrate, or which we denote as sigma t. And now in the aperture illuminated by a plane wavefront or parallel light, aperture scatters plane waves such that which are collected by the lens. Okay. This scattered, and okay, the scattered light in this direction, with and the scattered light in the parallel rays that is going to the lens will focus at a particular point. Similarly, this guy, this green light, that is undeviated light, will focus on this, and also parallel rays. These two denoted by the purple line, they are going to focus on the screen again. So all the parallel lines will focus at the same point, and that is the electric field distribution across the aperture, known as the aperture function, is transformed by the lens into the far field diffraction pattern. And that is what you will see, this intensity as intensity, these points you will see as intensity redistribution on the Fourier plane. Now, in the case of a circular aperture, okay, suppose you have this aperture is circular aperture, then because you have a plane wavefront and also the intensity is uniform across the wavefront, and therefore the refracted field will be a Fourier transform of the circular aperture. And we have seen in the diffraction case that it will transform into a Bessel function, or the Fourier transform of a circular aperture or top hat profile will be a Bessel function. And suppose you have a triangular profile for the laser beam, for as the aperture, then this will again be transformed into a sinc function. Then you may have a question, how could we make a triangular aperture? Okay, again it's going to be a top height profile, and therefore it's going to be a sinc square function. And this class was intended to make you familiar with some concepts of Fourier transform, and also how it can be applied, because we have seen that slit in this case will give you a sinc square or a sinc function as the at the Fourier plane for the electric field distribution. And if you Fourier transform an aperture function like this one, or a square wave or a square pulse like this one, then the result will be again a sinc function, which means diffraction and also this Fourier transform are one and the same. Or in other words, what we are trying to say is that we can Fourier transform the aperture function to see, or to see how the intensity at the Fourier plane is redistributed due to the presence of that particular aperture there. Okay, Initially you have some plane wavefront traveling in certain directions, and on a screen somewhere it will be like a uniform distribution. Whatever intensity distribution you had on this beam will be displayed here. But as soon as you put an aperture here, some sort of a restriction to its propagation, then the intensity redistribution on this plane here will change, and that is what we call the Fourier plane. And this intensity distribution is a simple Fourier transform of the function that you apply here, that you have here. Suppose in this case it is a square up, okay, it is let's say it is a rectangular aperture, and in one direction you also apply certain refractive index gradient. Then it becomes interesting, because simple application of uh, Fresnel integrals or Fresnel formula may not be easier to apply, and in that case you will be able to use an appropriate aperture function here, and then if we transform it to see how it will look on the Fourier plane. The one of the things which I may keep uh, uh, repeating is the aperture function, which uh, you know what it is, you are familiar already. Now you will see something called Fourier plane. It is a plane at which the intensity distribution is Fourier transform of the aperture function. And then you have, I will talk about something called image plane. When you consider imaging using a lens, this Fourier plane is, if you are using a lens, it is the focal plane, but image may not be formed at the focal plane. That could be something different. You know that if it depends on where your object is with respect to the lens, and you know that, okay, and magnifications and image formation, all these things, you know, and this aperture function, Fourier plane, image plane, they are all uh, to be clear in your mind. Okay, thank you.